Okay, the technical difficulties have been resolved, so let's go on to graphing our system of inequalities. So we're going to find x and y intercepts, and we are going to only shade that overlapping region. So we'll go piece by piece. I'll start with 2x plus 3y is less than or equal to 18. So again, I'm going to use that cover-up method. So I'll cover up the y's. That gives me 2x equals 18. So the x-intercept is 9, 0. And then cover up the x's. 3y equals 18. So 0, 6. And then my second one, cover up the y's. I get x is 15. So 15, 0. And cover up the x's. 3y equals 15. So that'll be 0, 5. And then cover up my y's, 2x equals 14, so 7, 0, and cover up the x's, y is 14, so 0, 14. And when you're making your own graph, you're going to want to go ahead and find all of your x and y intercepts before you mark off your axis so you know how far you have to go. So I know that I have to go out to 15 on x and up to 14 on y at least. So that's going to help me. We'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm going to go ahead and mark that while I've got it counted up. That's 14, 0. And then count over on this. So 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So my first inequality, my intercepts were 9, 0, and 0, 6. So that was my green one. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, 0, and 0, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Just want to make sure. And I'll connect those. And then I need to test to see which side to shade. So if I test 0, 0, that will give me 0 plus 0 is less than or equal to 18, which is true. So I will be shading that in towards the origin there. My second one was 15, 0 and 0, 15. So I had counted only over to 15, so 15, 0 and 0, 5. 1, 2, 3, 4, 5. Connect those. Test 0, 0. I have 0 plus 0 is less than or equal to 15, which is true. So I'll be shading that one in as well. And then my third line was 2x plus y is less than or equal to 14. So I had 7, 0 and 0, 14. I already have 0, 14 marked. 1, 2, 3, 4, 5, 6, 7. Connect those. And test 0, 0. 0 plus 0 is less than or equal to 14 is also true, so that will be shaded in as well. So my feasible region is going to be the overlapping region created by those inequalities. Remember, the first two just restricted me to quadrant 1, so I didn't even have to graph anything for those. My feasible region is going to be below purple, below green, and below blue. So it's just going to be this section in here. Remember that this overlapping region bounded by the inequalities is called the feasible region. The feasible region is the region that satisfies all of the constraints simultaneously. So any point in here, Bubba would be able to make the combination of riders and rovers based on the supplies he has. So he could make 1 rider and 3 rovers, or 4 riders and 1 rover. Any combination will work. But we want to find the combination of riders on the x-axis and rovers on the y-axis that is going to give Bubba the most profit. Now, do you remember where those points are located? Out of all those millions of reasons, or all those millions of combinations, the best combination, the one that will give him the highest profit, will be at one of these vertices. There are 1, 2, 3, 4, 5 vertices. Now, the vertices, some of them can be found just by looking. So that's our next step, is going to be to find the vertices of the feasible region. Sometimes we'll have to show work and other times we won't. For example, this vertex is just going to be at 0, 0. We don't have to do any work to find it because it's right there at the origin. This one right here was one of our y-intercepts. It was 1, 2, 3, 4, 5. So that one was 0, 5, and we don't need to do any work to find it. Similarly with this one, that one is at 7, 0. But the other 2 vertices, the 2 remaining ones, we do have to do some work for. So we're going to set up a system of equations for the green line. So if we're looking for this one right here, the green line, which was 2x plus 3y equals 18, and the blue line right here, which was x plus 3y equals 15. And we'll solve that system of equations. It looks like I can use elimination if I will multiply this second equation times -1. So that's going to give me 2x plus 3y equals 18 from the first one, and then negative x minus 3y equals negative 15 from the second one. So when I add those together, I get x, those go to 0, equals 3. So I'll have 3, comma, I'll substitute 3 back in, so 2 times 3 plus 3y equals 18. So that's 6 plus 3y equals 18. So 3y is 12, which means y is 4. So 3, 4 is that vertex right there. And then we're going to do a similar process to find this vertex. This vertex is the intersection of the green line, which was 2x plus 3y equals 18, and the purple line, which was 2x plus y equals 14. Now we could solve this by substitution, or we could solve this by elimination. I think elimination sounds good. Again, I can multiply the second equation by -1. So I'll have the original first one, 2x plus 3y equals 18, and then negative 2x minus y equals negative 14, which gives me 2y equals 4, so y is 2. So I have the ordered pair 2 for y, so something comma 2, and I can substitute that back in to give me 2x plus 3 times 2 equals 18. So 2x plus 6 is 18. So 2x is 12, which means x is 6. So 6, 2 is that other vertex. So each of these vertices represents a production level. For example, 3, 4 would mean that Bubba is producing 3 of the x coordinates, which are riders, and 4 of the y coordinates, which are rovers. Now Bubba makes a profit of $15 on each rider and $30 on each rover. That is what our objective function goes with, because we want to maximize profit. So remember, we had talked about that earlier. The objective function here is related to profit, So he makes $15 on a rider, $30 on a rover. Since riders are represented by X's and rovers are represented by Y's, the total profit is going to be equal to $15 times the number of riders he produces plus $30 times the number of rovers he produces. So the objective function is profit equals 15x plus 30y. This function is known as an objective function. The objective function is the function that you are trying to maximize or minimize. In this case, the objective is to maximize Bubba's profit. The maximum and minimum value of the objective function will always occur at a vertex of the feasible region. So we need to substitute each vertex of our feasible region into the objective function, and we will need to show work as we do that. So we'll have 0, 0. For 0, 0, the profit will be 15 times 0 plus 30 times 0. Of course, if he doesn't make any bikes whatsoever, his profit will equal 0. Next vertex, 0, 5. So profit would equal 15 times 0 plus 30 times 5. Well, 30 times 5 is 150, and this goes to 0, so this profit would be 150. At the vertex 7, 0, we'll have profit equals 15 times 7 plus 30 times 0. This part goes to 0, and then 15 times 7 is 70 plus 35 is 105. Next vertex would be 3, 4, so profit will be 15 times 3 plus 30 times 4, which is 45 plus 120, so 165. And our last vertex is 6, 2, so profit would equal 15 times 6 plus 30 times 2, and 15 times 6 is 60 and 30, 90, plus 30 times 2, which is 60, so this is 150. So it looks like Bubba is best off making this $165. That's the highest amount. So when we go to answer our question, it wants to know what is the maximum profit Bubba can earn and how many riders and how many rovers should he make in order to maximize his profit. So we'll want to say Bubba can make $165 profit at most. He can do this by producing, well, our ordered pair was 3, 4, and the x coordinates were the number of riders assembled, and the y coordinate was the number of rovers. So if he produces 3 riders and 4 rovers, so Bubba can make $165 profit at most. He can do this by producing 3 riders and 4 rovers. There's lots of different ways you could say that sentence. I might have said, Bubba should make 3 riders and 4 rovers in order to reach the maximum profit of $165. But you need to be specific when you write your sentence in stating the reason why he should do what you're telling him, because the reason why is so he can make the most profit he can, and how he should do that.